Okay, so I did WebAssign 4A, number 18, and the problem said an inclined plane of angle 20 degrees has a spring of force constant 470 newtons per meter fastened securely at the bottom so that the spring is parallel to the surface. A block of mass 2.39 kilograms is placed on the plane at a distance 0.324 meters from the spring. From this position, the block is projected downward towards the spring with a velocity of 0.75 meters per second. What distance is the spring compressed when the block momentarily comes to rest? So, the first thing I do is draw a picture. You have the block, and you have the angle, you have the spring, then the distance, and the velocity is going downward. So let's just write down all of our givens. We know theta is equal to 20 degrees. We know the spring constant is 470 newtons per meters. We know that the mass is equal to 2.39 kilograms. We know that the distance is 0.324 meters. And we know that the velocity is equal to 0.75 meters per second. So since the incline is frictionless, mechanical energy is equal to 0. And this means that the total initial energy will be equal to the total final energies. So that means all the energy it has at the top, the kinetics potentials, should equal all the energies at the bottom when the spring is compressed. So it's asking us to find the distance that the spring is compressed when the block momentarily comes to rest. So we know that. So we can use the equation. Since it has kinetic energy at the top, we can put the kinetic energy, which is 1/2 mv squared. And since it's elevated, we can say that it has gravitational potential energy, which is mgh. We can set that equal to, since it'll have spring potential energy, so we can say 1/2 kx squared. Then we're going to subtract mg x sine of 20. So that would be the equation, and we're solving for x. So plug everything in. We get that 1/2 is equal to 2.39 kilograms times 0.750 meters per second squared plus 2.39 kilograms plus negative 9.8 meters per second squared. Gravity plus 0.324 sine 20 degrees. So what we did here is we said that the height, since it doesn't give us the height for the potential energy, for the gravitational potential energy, we can set it just equal to the d sine of 20. It's a simple trig. So it'd be opposite over hypotenuse. And this is where some students tend to mess up, is they don't really know how to find the height, and it's just, you just have to apply trig. So the height would be the height. This is d, opposite over hypotenuse. Get this for h, and then we plug in for d, 0.324 meters, and this is all equal to 1/2 470 for the spring constant, newtons per meters, and then x, which will be meters squared, and we're solving for x, minus 2.39 kilograms times negative 9.8 meters per second squared times another x, and then sine of 20 degrees. Okay, so that'd be the height at when the spring is compressed. The height would be x, which would be this distance when the spring is compressed. This is also where some students mess up, is they can't find the height for when it's compressed, or they'll use the height over here when they're not supposed to. So x would be x sine of 20 is equal to the height when the block is at the bottom compressing the spring. So now, solving all this out, we get that it'll be a quadratic, so it's a negative number and then a positive number, but since we're dealing with distance, you need to pick the positive number, and that came out to be 0.136 meters as your final answer. So basically, where some students mess up are these parts where they have to find the heights. So you just have to apply a simple trig to it and make sure that the different heights are, because they're different heights, so you have to make sure you're not plugging in the same height for both of them.